for first, let me just, I think rather than definition, no? So let me put like this. It's a point where whole mass appears to be concentrated. Appears to be, hypothetical it is, appears to be, I'm writing it, appears to be. So next again, second one. It's a unique point at the center of a distribution of mass in space that has the property that the weighted positions okay, just wait, some, I think some software giving problem. Yeah, well, position vectors relative to this point sum to 0. So or in a simplistic COM, I'll call it in short. Is the mean location of distribution of mass in space. Several ideas what we can put it. So what is actually the meaning of all this? So you take an object. So what is this object made up of? It is made up of shapes. So let this be the object here. Now, what actually this object, can I assume it? Can I assume it made up of different particles? Okay, let me take this a particle M1, M2. Though it's a particle, I'm just showing a block so that it'll be easy for you. So can we assume that it is made up of like this? This is having M1G. So the weight of this M1G will act vertically down. M2G, M3G, M4G, M5G. How do all these forces will be acting? Will be vertically down. M7G, M8G. Show that forces like this. So this is the M8G. The weight of all that we like to. So let me take one point here now. Let me take some reference point. So from that reference point, I can now define the position vectors. R1, I'll show only few. R2, R3, R4. So what is R1? This is R3, this is R4. Similarly, you can define for R2 also. Let me write, this is 3, this is 2. So can we, with respect to some reference point, so there's a reference point. Can I define the position vectors? These are particles, huh? To make you understand, I'm just showing like a body, that one. These are very small, tiny particles. This one. So now I'll find out the torque due to all that one. So what is the torque acting about point? So tau 1 plus tau 2, tau 3, tau 4, and so on till tau n. This is the net torque. Torque means which will produce the rotational effect. Time being, those who are not having idea, just only listen. Those who are having idea, you can analyze here. So the weight of the particles, what happen? The weight of the particles, what happen? They'll set up a torque, and the resultant torque is given by that one. So now there is another way of finding out the resultant torque. So what this resultant torque is telling? The total mass of the particles into g. This should be, there's a vector mg bar into, this is saying RCM bar. What is tau 1? Tau 1 in simple sense, m1g bar m1g bar into r1 bar. So and okay, we'll do one thing. There's a basic definition of this one, mg bar, because mg bar, or you can write w bar, you can write it. So mg bar cross rcm bar, it will be like this one. So now the resultant, the net torque can be obtained like this. So what is rcm bar? It's telling like some effective weight. So effective position, I'll call that one. So what is rcm bar? Rcm bar, we can define it as, just as a definition. If I just write one formula, you'll find very difficult. So those who are having, so what is RCM bar? This one. So what torque is set up by the particles, by the weight of particles about reference point. The same resultant torque can be determined by taking the net mass of the system, the gravity g bar as it is, and RCM bar. What is RCM bar? Look, position vector of center of mass from the reference point. What is RCM bar? Position vector of center of mass, this one. And what are r1 bar, r2 bar? They are the position vectors of the particles from the reference point. So what is r1, r2 bar, r3 bar, and so on? Position vector of particles from reference point. So this we will, what we do is, this everything what will happen? This everything. So we can write this, because the g bar will cancel out. G bar will cancel out, and the angle between m bar and r bar is such that this one, so we can write it m1 r1 bar plus m2 r2 bar, m3 r3 bar, so on, m1 r1 is equal to m into rcm bar. So finally what will happen? I'll end up with this equation. So what is that rcm bar? Position vector of the center of mass. And what is m? M is the total mass of the body. M is equal to m1 plus m2 plus m3 and so on. So there is a meaning here. So what is telling? So if you look at the definition, what it says, like, it's a unique point at the center of a distribution of mass in space that has the property that the weighted position vectors related to this point sums to 0. This is the one thing. So now, okay, this is about only definition. Okay, let's proceed further. Let's explore further. So after this, so what do you mean by, why do we are giving so much of priority here? So, and you look at the first point. What the first point says, it's a point where the whole mass appears to be concentrated. So again, what this definition is telling, appears to be, not like it will be there. It appears to be. So this aspect is what we are going to take help in studying the center of mass concept. So now, what is a direct advantage or what is the use of this one? Suppose if I take some object here. Look at now where the center of mass. So let's assume that the center of mass will be somewhere in this region. I'm going to spin and I'm going to throw it. All of you know spinning is going to spin and also move in a path here. So after some time, the object, okay, let it come like this. So now look at this particular thing. So that center of mass, what will happen? So let me, how the object, it is spinning as well as moving, no? It is spinning and also it is moving. So it is having both, I'll say translatory as well as rotatory. So look at the object is having both. Body is having translatory and rotatory motion. Rotatory motion about what? About the center of mass. All the particles are rotating about center of mass and center of mass is moving in some path. This is what? Path of center of mass. Means there is it's a hypothetical point. Don't think that again, sir, I'll go and remove that center of mass. No, it's like a point. It's a hypothetical point about which all particles will rotate here, and it's going to describe the translatory motion. When object is having both rotatory as well as translatory motion, then the center of mass is going to describe a translatory motion. A good example, like you take any arbitrary shaped object, you spin and throw it, then it's going to spin, it's going to spin, you can see it's going to spin, and also it is moving down, no? It is describing some path, it's having some displacement. Then the center of mass will describe that translative motion. This green color is called as a translative motion. What do you mean rotative motion? About you take any point, here that one, look at that point. Shall I say it is rotating about center of mass? The point P is rotating about center of mass. What is center of mass? The star mark. Star mark is a center of mass. So like this in all numericals, you try to locate like a where all center of mass, then put just star mark. So this what happens for like a body which is having translative motion. So therefore, what are the very important features like the center of mass describes the when a body is having it's like a complex motion. We'll call this a complex motion. The center of mass is going to describe a translatory motion. This is another third point. I'll summarize here. Fourth one, the center of mass describes the translatory motion. Or one more thing. So if you take again an object, tire, what is this? So it will be V and omega. So all of you, what is this? The wheel of a vehicle. Take example. The center of mass open here is going to describe translative motion. Whether all points will rotate about the axle. And what about the axle? Axle will be moving forward. Of course, you don't see that. You see all points are rotating. What is that center of mass again? It's a hypothetical point which will be there in the body, which will describe only translatory motion. So we just call this as C. So here, who is the center of mass? No, center of mass will describe transmission. So this we can call it as a rolling motion. So the motion of a wheel of a vehicle is what? There it will have a rolling motion. In that development, the center of mass is going to describe translative motion. Translative motion means not something straight line. Later in rolling motion, we are going to show difference between translate and rotate. Time being, you can take these examples. After this, we have further. I'm just summarize point was so that it will be easy for you. There's a difference between we have center of mass. So it is used to describe translative motion. What about we have one more word called as center of gravity. So what is center of gravity here? Center of mass, it is used to describe translative motion where the whole mass appears to be concentrated. What about center of gravity? Center of gravity is what we show now for an object, mg will act. So let's take an object. The weight of the object will act here. So what is mg? Why we have to show the center of gravity? You break up this object into several parts. And what is the weight? The weight is a vector quantity. The vector sum of weight of different particles. That only, no? Center of mass will describe only translative motion. What is the weight? How you define? So we'll call center of gravity. The symbol what we use is Cg. Now, if you take the different particles, let's assume body is made up of different particles. The weight of particles will act. So what is center of gravity here? So shall I say that it's a mean position through which the weight of a particle will pass through, or the effective weight of a particle will act. So here I think the definition slightly will change. Center of mass, center of gravity. It is a point through which effective weight of particles will act through. Center of mass is not like that. Center of mass, we don't define center of mass in that way. But if you go for the books, no, center of mass, center of gravity, both are same for objects what we are going to study that one. Any reason for that? But the definition is saying something. What is center of mass here? It's a hypothetical point about which the whole mass appears to be concentrated. What center of gravity is not like that. It is a point through which the effective weight will act through. And in another sense, center of mass, what you can say, the algebraic sum of moments about that point must be 0. So we do define like this, different ways here. Now, so then both are different. Again, I'll say that again, there's a center of mass here. For the objects, 6 point, I'll write one important for the objects. For the objects located on the surface of Earth, center of gravity and center of mass lies at same point. Okay, that's something I'm putting for the objects located on the surface of the Earth or somewhere at a height of even you can say 500 meter or even 20-30 kilometer. No, for the objects located on surface of the Earth, center of gravity and center of mass lies at same point, but they're having totally different property. Any reason for that? Because the gravitational field is uniform. We take g equal to 10 meter per second square, no? Almost till 100 kilometer, it is assumed. We take almost g to be variation is very small. So the center of gravity and center of mass will be different. If the gravitational field is non-uniform, then center of gravity and center of mass need not to lie at same point. In uniform gravitational field, The center of gravity and center of mass will lie at same point. In non-uniform gravitational field, center of mass and center of gravity will be different. Suppose what is our planet? Our planet is Earth, no? Our planet is spherical in shape. So what is the gravitational field produced by the spherical object on the surface of the Earth will be uniform. So therefore it will be same. If the planet is some sort of like a arbitrary shape here, then at different points the field will be different. Okay, getting this one? In that case, the object is said to be present in a non-uniform gravitational field. Then the center of gravity and center of mass will be different. So, but most of the planets, what we have, all are what? Spherically symmetrical, no? They're symmetric about the spherical point. So therefore, for our consideration of center of gravity, center of mass, and that's why in the books, no, some books they called even center of gravity. So don't get confused here. Okay, this is about things. So now what we say like center of gravity is point through which effective weight of particles will act for the objects located surface of center of gravity and center of mass lies at same point. Even in books, even in advance, if they say calculate center of gravity, also take it to be same. I'm making things clear. Then what is use of center of gravity? Center of gravity, I'll use symbol COG, center of mass COM. Next property like center of mass, it is used to define translative motion. It is already we defined it to define translative motion. What about center of gravity? It is used to define equilibrium of bodies. See, the center of gravity definition only is taken and we are defining center of mass again. So you should not get surprised here, because earlier what I did first M1 G1 R1 M2 G R2, the torque set up by the weight of individual particles, that resultant torque is nothing but the torque set up by the effective weight of the particle. I think I took the definition help of center of gravity only to define center of mass. The reason for that, because the field is uniform. Field is non-uniform, then center of gravity, center of mass will be different. Location will be different. Again, the location of finding this location of center of mass, the method is same. Are you getting? No? Okay, now let's not bother like in non-uniform gravitational field. So totally let's leave that topic. It's not there even for our syllabus also. Only when you go for higher particle physics, there we are going to study that. So two different points are there. Center of mass, it is just related to something translative motion. What is center of gravity? It is something related to equilibrium of bodies. So when we enter into the same rotative mechanics, when it comes equilibrium, I'll take center of mass only again. When it comes rolling motion, I'll take center of mass. Though the equilibrium I should define about center of gravity, but still I say center of mass. Both what happen will be we use it in same sense, but the properties are totally different here. So now time being, you can just forget center of gravity. You don't know anything, leave it. You know only center of mass and get into the problem. And the center of mass of body, what will happen? Center of mass can lie inside or outside the body. Later on, as we do numericals, you can come across this condition. Center of mass can lie inside or outside the body. So these are some basic properties of the center of mass what we are using. So now what is our entire discussion is somehow what happened, we should calculate the